Greetings everybody. This is the first video for part 3 of the chapter 8 lecture notes, and it deals with two-dimensional collisions. And so remember, momentum is a vector. When we write P equals mv, it's a vector. And again, if momentum's conserved, we have P initial equals P final. Well, remember now we're doing collisions in 2 dimensions, so we have to, when we say Pi equals Pf, what we mean is Pxi equals Pxf, meaning the initial momentum in the x direction must equal the final momentum in the x direction, and likewise for the y. Pyi equals Pyf. The initial momentum in the y direction must equal the final momentum in the y direction. Well, here's a pretty straightforward example of a two-dimensional collision. We can see here at this intersection, you have a car and a truck collide. The car is the blue. It's moving in the positive x direction. Before the collision, it's moving in the positive x direction at 25 meters per second. Call that M1. That's the 1,500 kilogram car moving east, i.e. moving in the positive x direction at 25 meters per second. Well, now M2 is this truck, this 2,500 kilogram truck traveling north at 20 meters per second, meaning before the collision, it's moving in the M2 is moving in the positive y direction. So again, M1 is the car, which is the blue. Before the collision, M1 is moving in the positive x direction. Before the collision, M2 is moving in the positive y direction. They collide at this intersection. They stick together, so they undergo a perfectly inelastic collision. So they stick together. So they move as one object of mass M1 plus M2, and they move with some final velocity Vf, indicated by this red arrow. They move with a final velocity Vf, and Vf makes an angle of theta with respect to the positive x-axis. Well, Vf, the final velocity of the system, of the two cars, which are now stuck together. Well, Vf will have an x component indicated by the blue. That's going to be Vf cosine theta. And Vf has a y component indicated by the green. That's going to be Vf sine theta. Okay? Remember, they move off. It's a perfectly inelastic collision. So again, M1 is the blue car with Vx, its initial speed, V1 xi, is 25 meters per second. Don't let the subscripts throw you. Just V1 xi just means it's the initial speed in the x direction. Okay, so M1 V1 xi. Now we have M2 is moving in the y direction, so we have M2, and then we have V2 yi. That's the initial speed in the y direction. Okay, perfectly inelastic collision. So now we need to set Pxi equals Pxf and Pyi equals Pyf. Well, I'm actually going to do conservation of momentum. I'm going to write the y equation first. So Pyi equals Pyf. So the initial momentum in the y direction is simply M2 V2yi. Now the final momentum in the y direction, it's M1 plus M2, and then it's Vf sine theta. Because Vf sine theta, that's the y component of Vf. So I have M2 V2yi equals M1 plus M2 Vf sine theta. That's equation 1. Now again, x direction, Pxi equals Pxf. Well, the initial momentum in the Pxi is M1 V1 xi. It's M1 times V1 xi. The final momentum in the y direction is M1 plus M2, and then Vf cosine theta, the blue. The x component of Vf is Vf cosine theta. Now, why did I decide to write them in this order? And so why did I do Pyi equals Pyf and then Pxi equals Pxf? Well, look at equations 1 and 2. What if I take equation 1, take equation 1 and divide equation 1 by equation 2? Well, on the right hand side, when I take 1 divided by 2, the term in parentheses cancels, the VFs cancel, and sine divided by cosine is tangent. Okay, so I get on one side I get tan theta. Then on the other side I get m2 v2yi divided by m1 v1xi. Okay, so I get that. And again, why are we doing this? Well, I want the direction and magnitude of the velocity after the collision. So I want the direction and magnitude of VF. That's what I'm solving for. So again, going back, how did I get equation 1? Conservation of momentum in the y direction. How did I get equation 2? Conservation of momentum in the x direction. Now again, when we talk about direction and magnitude, I want the direction, I want the angle. I want to know what is theta. We can see that VF is in quadrant 1, but I want to know, when I say direction, I want the angle. So notice, that's why I did this. Again, when I take equation 1 and take 1 divided by 2, well, notice on the right-hand side, the term of parentheses cancel, and the VFs cancel, and sine divided by cosine is tangent. Then on the other side, you just have m2 v2yi divided by m1 v1xi. Okay, so if tan theta is this, then theta is simply equal to the inverse tan, or the arctan. So theta is equal to the arctan of m2 v2yi over m1 v1xi. Well, plug in the numbers, and you get that theta is equal to the inverse tan of 4/3, which is 53.1 degrees. Now, once you know theta, you can use either equation 1 or equation 2 to get VF. And I used equation 1. I want VF by itself, so divide both sides by the m1 plus m2 and then the sine theta. So this is what you get for VF. Plug in the values and you get 15.6 meters per second. So this is a very common two-dimensional collision problem. In this case, it was perfectly inelastic, meaning the cars collide, they stick together, they move off with some speed VF at some angle theta, and that's what I'm looking for. When I say direction and magnitude, direction is the angle theta, and then the magnitude is simply what is VF. Now another one. Let's check the time here. Okay. Now let's look at a very similar problem from one of the practice tests. And here's an asteroid collision. And so you have asteroid A collides with asteroid B, but asteroid B is initially at rest. And then, so asteroid B is initially at rest. So asteroid A collides with B. So after the collision, asteroid A moves off with some final speed we'll call VA final, and VA final moves at an angle of 30 degrees above the positive x. Asteroid B moves off with some VB final, and VB final moves at an angle of 45 degrees below the positive x-axis. And so notice, after the collision, asteroid A, it has a speed of VA final, and VA final makes an angle of 30 with the positive x. So then you have the x component of VA final. It's right here. I've drawn this little dotted arrow showing you that component. That's that blue. That's the x component of VA final. That's VA final cosine theta. I'm letting theta equal to 30, and I'll call the 45-degree angle, I'll call that phi. Okay, so VA final, that VA final makes an angle of theta. VB final makes an angle of phi. And theta is 30, phi is 45. Now VB final, well, the x component of VB final right here is VBF cosine phi. That's this vector right there. See, I'm saying, hey, notice, guys and gals, that's the x component of VB final. It's VB final cosine phi. The red, that's the y component of VB final. That's VBF sine phi. The x component is cosine, y component is sine. And again, conservation of momentum in the x and y direction. And again, asteroid B is initially at rest. Okay, so here's conservation of momentum in the x direction. And we don't worry about the masses because the masses are equal, so the m's will all cancel. So you have VA initial, that's the momentum, the initial momentum in the x direction. Remember, asteroid B initially at rest. So the initial momentum in the x direction is VA initial. The final momentum in the x direction is, notice right here, is VA final cosine theta plus VB final cosine phi. Remember, the asteroids have the same mass, so the masses will cancel, so you don't need to worry about them. Now, in the y direction, the initial momentum in the y direction is 0. Why? Because, remember, asteroid B is initially at rest. Asteroid A is initially moving in the positive x direction. So there's no initial momentum in the y direction, so it's 0. Now, the final momentum in the y direction is VA final sine theta minus VB final sine phi. Remember, the y momentum of asteroid B is negative. See, because clearly VBF sine phi is negative. Okay, so you have two equations, and again, what I want is in this case, I want the speed of each asteroid after the collision. I want VAF, and VBF. Okay. Well, what I did is I solved equation 2 for VBF. I got an algebraic expression for VBF, and I put that expression for VBF, I put it into equation 1. See, right there. And that's how I got this equation right there. So I solved equation 2 for VBF, took that expression for VBF, put it into equation 1, and I end up with this equation. Okay? And, well, and so then notice here in the second term, cosine phi divided by sine phi is cotan phi. Okay, so I get equation 3. VAI is equal to VAF cosine theta plus VAF sine theta cotan phi. Well, solve this for VAF, and you get this expression here, and plug in the numbers, and you get VAF is 29.3 meters per second. Then, once you know VAF, you can, again, once you know VAF, you can use equation 2 to get VBF. Well, we solved for VBF. Once you get VAF, you put it into that expression and get VBF. And then in part B, I want to know what fraction of the initial kinetic energy is dissipated, how much is lost, in other words. Well, percent lost, percent dissipated is, what they mean is you take the difference, you take the final minus you take the initial minus the final, divide by the initial, and then multiply times 100. So the initial kinetic energy is VAI squared. The final kinetic energy is VAF squared plus VBF squared, then divided by the initial VAI squared, and times 100. You get 19.6. But it's just, you know, that's the percent dissipated. But again, this is a two-dimensional collision. So, and this is the conservation of momentum in the x direction, and this is conservation of momentum in the y direction. Let me go ahead and save this video and get it posted.